like to present to you the implementation of a multi-stage analytical framework for the study of integral type functions. In part 1, we introduced the methodological framework of the proposed multi-objective approach. The aim of part 2 is to move from methodology to implementation. Here, we demonstrate the practical application of the approach through a detailed multi-stage analysis of a representative integral type function. The analysis is structured and intended for classroom use. Before moving to the implementation, I will briefly recall the main elements of the method introduced in part 1. The approach is based on the simultaneous teaching of function analysis and improper integrals, which are usually treated as separate topics. The core working unit is a multi-stage problem decomposed into a sequence of interconnected analytical stages. The partition of unity is used here as a pedagogical principle, providing a structured way to organize these stages without losing the global view of the problem. Here, the partition of unity is realized through alternative analytical paths, chosen according to students' prior knowledge. This brief reminder is intended only to fix the context, so that we can focus next on the concrete implementation of the method. At this stage, we select a representative integral type function. It is defined by an improper integral and has no elementary antiderivative in general. This makes direct computation impossible and necessitates the use of estimation and limit techniques. The choice is intentional, as it allows the full sequence of classical function analysis while supporting systematic work with improper integrals. In the following slides, the function is analyzed step by step within a multi-stage framework. The analysis follows a fixed multi-stage structure. It then proceeds through asymptotic behavior, symmetry, intersections with the coordinate axis, monotonicity, and extrema. Finally, the range, convexity, and graphical representation of the function are presented and summarized. The analysis begins with the integrand. The properties of the integrand determine the domain of definition of the integral function. A singular point occurs at x equals 0, which requires separate consideration. Since the limit of the integrand exists at this point, the value can be extended by continuity. As a result, the domains of the integrand and of the integral function are determined. This completes the analysis of the domain of the function. Limits at the boundary points of the domain are examined at this stage. The distinction between the two approaches arises from the analytical structure of the integrand and from the level of analytical tools available to the students. In the first scenario, the boundary limits are analyzed using direct estimation and comparison techniques without relying on power series expansion. This approach typically reveals conceptual difficulties related to improper integrals and limit behavior near singular points. In the second scenario, A suitable transformation reduces the analysis to the classical Basel problem, which concerns the exact summation of the series, sum 1 over k squared, and requires additional analytical tools. Both approaches address the same analytical question and differ only in the methods employed, which allow students with different backgrounds to work within the same stage of the analysis. The asymptotic behavior of the function is examined through limits at the boundary points of the domain and at infinity. The analysis of the boundary limits shows that no vertical asymptotes occur. Limits at infinity are then considered and exclude the existence of horizontal asymptotes. The existence of a slant asymptote is examined by analyzing the asymptotic slope, which is shown to be equal to 0. Consequently, no slant asymptote exists. Therefore, the graph of the function has no asymptotes. Symmetry properties and intersections with the coordinate axis are examined. The domain is not symmetric with respect to the origin. Therefore, the function is neither even nor odd. The analysis further shows that the graph does not intersect the coordinate axis. The derivative has a very simple form. Since the function is positive on the whole domain of the function is strictly increasing and therefore has no extrema. The range of the function follows from the monotonicity and the boundary limits. Analyzing the second derivative shows that the function is strictly concave on its entire domain and therefore has no inflection points. The results of the multi-stage analysis can be synthesized in a summary table and a graph. The table summarizes the size and the behavior of the function. The table brings together the results from all previous stages. The graph is generated from the analytical properties identified in the previous stages. The graphical representation confirms the analytical results. Together, the table and the graph offer a coherent overview of the analysis. This overview supports a clear interpretation of the results. The didactic implications of the approach can be summarized as follows. By reducing knowledge fragmentation, the approach supports structured reasoning in mathematical analysis and guides students through complex problems. At the same time, its multi-stage structure offers flexibility for instructors. The stages are logically independent, which allows the analysis to continue even with partial results and enables adaptation to different levels and teaching scenarios. This also provides a clear indication of students' level based on the stages they are able to complete. These outcomes confirm the educational value of the approach. In conclusion, the proposed method is successfully implemented in practice. The multi-stage analysis supports the simultaneous teaching of thematically related methodological units. The approach links different analytical procedures within a structured framework. It builds a clear bridge between theory and teaching practice. These results complete the implementation phase of the proposed approach. Thank you for your attention.